Hello friends, welcome back. So far we learned about basic terms of thermodynamics like heat content, enthalpy, work done and change in internal energy. Now using all these concepts we learn how to calculate work done in different processes. So let's start the session. Hi friends, in the previous part we have discussed about enthalpy and its role in thermodynamics. In this part we will discuss about different kinds of processes. The first is isothermal reversible expansion of ideal gas. So what does that mean friends? This process is isothermal in nature, that means temperature at any state remains constant. Next important is reversible. So what do you mean friends? What does that mean? It means that the system can be brought to its initial position. Next friends, expansion. The gas is expanding, right? So that means work is done by the system and the gas is considered to be ideal gas. Alright, so consider now the same example, the same best example we had discussed in past also. This is piston and this is the gas molecules. Friends, the important point which you have to understand is this kinetic energy of the gases, right? So the kinetic energy of the gases depends on temperature only, right? And what does that mean? The internal energy, right? The internal energy will be zero if the temperature remains constant. Why friends? If the temperature is constant, kinetic energy is constant and also internal energy will also be constant, right? In that case the change in internal energy will be zero. So in any isothermal process, the change in internal energy will be zero. So this is first important point you have to understand. Next important point you have to understand is that P1 will be equal to P2, because you know that from the gas laws, if I plot PV is equal to constant, you will get such kind of a graph. And what you know that friends? Know that in this process where PV is equal to constant, P1 V1 will be equal to P2 V2, right? So if that happens friends, what is work done? I told you, right? Work done is integral of P dV. So what does that mean? That it means that there is no change in volume and the pressure. So there is no change in the product of pressure and volume, right friends? So what does that mean? It means that P1 V1 minus P2 V2 will be 0, right? So what does that mean? This will be 0, right? So what happens friends? The change in enthalpy will be 0. So in any isothermal reversible expansion of ideal gas, the change in enthalpy will be 0. Next, calculation of Q and W. Let's calculate Q and W, right? So what do you know friends? You know that in isothermal process delta E is equal to 0, right? And imagine if it is a situation where work is done on the system, right? Work is done on the system. So what happens friends? If it is 0, the work done will be equal to minus Q. Friends, this is calculation of Q and W for only isothermal process, right? And remember friends, it is not given whether this is expansion taking place or compression taking place, right? So there is just given that it is isothermal process and we will calculate Q and W accordingly, right? And what through first law of thermodynamics you can develop a relationship that W is equal to minus Q, right? And imagine friends, let's assume that compression is taking place, that's why W is represented with a positive sign, that is plus W. And what is happening friends? It is now for isothermal process, it will be W will be equal to minus Q since delta E will be 0. right? So this shows that in isothermal expansion, work done will be equal to the amount of heat absorbed. If this is the compression taking place, right, and what happens friends in expansion, that too isothermal expansion, right? You again know the basic logic of first law, change in internal energy will be Q minus W, right? It is minus W because it is expansion you are considering here, right? And in that case delta E will be 0 and Q will be W. So in isothermal compression W equal to minus Q, and in isothermal expansion work done will be equal to heat absorbed, right? So friends, you have to remember that Q is the heat absorbed, right, and this will be equal to work done, this will be equal to work done in isothermal expansion, right, and this will be equal to heat liberated, W will be equal to heat liberated, right, in isothermal compression, right friends, in isothermal compression. And the work done can be calculated accordingly by minus nRT ln V2 by V1 or nRT ln P1 by P2. This is actually the work done in the isothermal process, right friends. And let's see the derivation, how you will get this. What you know friends, with the first law of thermodynamics, again you know, if it is expansion taking place, Q will be equal to W, right? So what will be W friends? W will be equal to change in pressure and change in volume, the product of change in pressure and volume. And what else you know friends? I told you, right, it can be written as PdV also, right? And if you get this value, and imagine the situation, the volume is taken from V1 to V2, right? And imagine this is the case now. So you have to now express this pressure in terms of volume so that you can integrate this. And how can pressure can be expressed in volume friends? Yes, you have a solution. That solution is ideal gas equation, where pressure can be expressed in terms of volume, that is P is equal to nRT by V, where V is the volume, right? So what you can do friends, now you can use this here as nRT by V dV, right? And you know the temperature is constant, R is constant, N is constant, and I can get them out of the integral part. So nR into T into, right, integral of V1 to V2 dV by V. And what this is friends, integral of V1 to V2 and dV by V, this is actually gives me ln V, right? And this is equal to, and integrals are from V1 to V2, that means nRT ln V2 by V1 gives me the work done. So work done will be, I am writing it here friends so that it will be clear to you. It will be nRT ln V2 by V1, right? And if it is V2 by V1, you can express in pressures also. It will be relative again, and it will be reverse. It will be ln P1 by P2. So the work done in isothermal expansion will be nRT ln V2 by V1, and if it is compression taking place, then you will get minus nRT ln V2 by V1. So this is because of compression, this is work done because of compression, right friends? And this is also because of work done by compression, and if it is plus sign, it is because of isothermal expansion taking place. So this is what, how to calculate work done. And if you know how to calculate work done, heat absorbed, can be calculated accordingly. So this is what, how to calculate Q and W in isothermal process. So friends, in this part we have discussed about isothermal process and that too isothermal reversible expansion of ideal gases. So we have discussed how to calculate heat content and work done in an isothermal process. In the next part we will discuss some more interesting points in thermodynamics. So keep tuned friends. Have a good day.